So far, we've seen microbes that nibble on polyethylene and bacteria that start chewing polypropylene. But there's another player in the plastosphere, one that's metabolically gifted, ridiculously adaptable, and not picky about your polymers. Meet Pseudomonas, a microbial survivalist found in soil, seawater, sewage pipes, industrial waste, even sterilized environments. It doesn't just break down plastics, it can colonize medical tubing, hospital catheters, even life support machines. A plastic eater, yes, but also, in some cases, a pathogen. Pseudomonas is a bacterial genus found from marine sludge to hospital sinks. Its species have been studied for decades, not just for degrading oil and solvents, but for tackling some of the toughest synthetic polymers ever made. Pseudomonas first gained scientific attention in the 1970s, when genetically engineered strains like P. putida were shown to break down oil compounds. A breakthrough later spotlighted during major spills like Exxon Valdez in 1989 and Deepwater Horizon in 2010. That same enzymatic machinery turns out to be useful against plastics too. This isn't about polyethylene anymore. Pseudomonas putida has shown the ability to degrade polyurethane, a plastic used in insulation, foams, and coatings. Pseudomonas mendocina has been studied for partial breakdown of PET, the plastic in water bottles and synthetic fabrics. Some strains even show signs of attacking polystyrene after oxidative pretreatment. How? This genus has a rich enzymatic toolkit: esterases, oxygenases, lipases, and sometimes lacases. These break down ester bonds, oxidize side chains, and create entry points into highly inert polymers. Unlike the slower bacillus and P. album, Pseudomonas can respond rapidly and adapt its metabolism to new substrates. In some cases, it even uses plastic-derived compounds as carbon sources. Real metabolic assimilation, not just surface erosion. And here's what makes it dangerous to synthetic polymers. It works in soil, seawater, brackish sediment, and even industrial wastewater. It doesn't need light. It can handle variable oxygen levels. And it thrives in contaminated environments where other microbes struggle. But its adaptability doesn't stop there. Certain strains, like Pseudomonas aeruginosa, are also pathogenic and known to colonize medical plastics. In hospital settings, it's been found feeding on the very materials used in catheters, tubes, and machines, which means this microbe isn't just a recycler. It's a resilient survivor that can thrive where sterility is crucial. That's not just fascinating, it's a problem. In lab studies, P. putida has degraded PU foam with up to 25% mass loss in under 30 days. At that rate, 99% of the material could be gone in less than a year and a half. For PET, the degradation is slower, around 0.5 to 1% over 60 days, depending on surface oxidation, which translates to full degradation in roughly 100 years, still significant for a plastic once thought eternal. For polystyrene, degradation rates are lower, but early studies show measurable oxidation and weight loss after UV exposure followed by bacterial activity. It's slow, but it's happening. And when working in consortia with other microbes, Pseudomonas performs even better. Co-metabolism speeds up breakdown. So what does this mean for plastics in the wild? It means that even polymers designed to resist weathering are not immune, especially once aged or pre-treated. And Pseudomonas is everywhere. It's not a specialist. It's an opportunist with a broad enzymatic playbook. If P. album was the patient fungus and Bacillus the persistent underwater digester, then Pseudomonas is the street-smart scavenger, faster, broader, and not afraid of complex chemistry. Next time, we zoom out and look at what happens when these microbes meet on the same fragment of ocean plastic. That's the plastosphere.